Hooray! This is the last section. And what it is it talks about how changes had to be made. I could make this very long, but instead I decided to just give you the facts, and I encourage you to come to Zoom lecture where I can talk a little bit more deeply about this, and also I know I'm going to have a lot of questions. So what they did is they went in the lab and did some experiments. And when they did some experiments, they had to make some modifications of this theory. So what we're saying is that when we have the 2s and 2p sigma and pi molecular orbitals, their interaction is going to result in some changes. All right, so I've always tried to present this. I always have a lot of questions. So let's just say the facts. If I have oxygen, fluorine, or neon, the diatomic molecules, they will have this order for their molecular orbitals. If I have boron, carbon, or nitrogen, they will have this order. Now, I'm kind of angry with the people that wrote the book because doesn't boron, carbon, and nitrogen come before oxygen, fluorine, and neon? It would be so much better visually to present it, but I'm using the picture from the book, the second order, and we're talking about how experimental. So I go to this next slide, which repeats that exact same picture. What they say is that mixing can occur because these levels are close in energy. Now you're a brand new student. You're going to say, how do you know this? Well, you just have to believe me. The sigma and the sigma star from the 2s, they actually are said to become more stable and they go down lower in energy. I have no problem with that at all. But the sigma and the sigma star from the 2p, they become less stable and they go up higher in energy. I'm just telling you what the theory says, okay? The net effect is to move the sigma 2p from below the pi 2p to above the pi 2p. And again, it's going to depend what the diatomic molecule we're talking about data has. So what I have here is the table from your textbook. I encourage you to utilize this table as you are working problems. And you really need to work problems because it's not just enough to know these facts, you must know how to apply them. You know, what's really important is this magnetic behavior. And what it is, it's in really, really fine print. Okay, so that also kind of has me a little bit angry. I mean, if it's very important, why do we have it as such small font? But what we have when we have paramagnetic is we have unpaired electrons. And I'm just circling them because I'll say there's only two cases. One is with the boron diatomic, one is with the oxygen diatomic. But what really brought this to the surface were these two diatomic molecules, which you are currently breathing. Nitrogen was found to have all the electrons paired. Oxygen was found to have two unpaired electrons. And we have a lovely demo that we always do in class, and if there's a video of it, I will play it to show how you can contrast the paired of electrons of nitrogen with the unpaired electrons of oxygen. Let us modify the molecular orbital energy diagrams. Know that as you proceed in science, like even with this course, we are giving you the fundamentals. The more is known, the more modifications need to occur, and that's how science works. So I hope you can take the basics from what are in this course and apply them when necessary to your upper level studies. When you're going to be asked to describe a molecule using molecular orbital theory, you will use all the electrons, you will place them one at a time in the lowest energy available, and that's what I did at the end of the last video. You will use the electron molecular configuration, you can use the energy level diagram, and you can note the magnetic behavior. You'll see that by populating it, and you can also calculate the bond order. Now, I'm not going to do each one. We would all fall asleep. But we know that beryllium has 4 electrons. If I'm making it diatomic, I multiply it by 2, and I have a grand total of 8 electrons. It only has s electrons, so I will arrange them in the sigma, the sigma star, the sigma star. There's two different groups because we have the n equals 1 and n equals 2 level. I will take my bonding electrons, which total to 4. I will take my anti-bonding electrons, which total to 4. And molecular orbital theory gives it a bond order of 0, which according to molecular orbital theory, beryllium, the diatomic we got does not exist. So again, I am not going to put you to sleep. What I did is I did every diatomic in that second period. I counted the number of electrons and I calculated the bond order. What I'm just going to show you is the important things. If I have a BB, boron diatomic molecule, it's paramagnetic. That's a fact for molecular orbital theory. If I have a carbon-carbon, it says it has a double bond and it says it's diatomic. If I have a nitrogen, it has a triple bond and it's diamagnetic. So with molecular orbital theory, we don't really see these two things, but we do see diatomic nitrogen. It's what you're breathing right now. It has the bond energy of 936 kilojoules. Again, molecular orbital theory accounts in the triple bond for nitrogen that you are breathing. If I look at oxygen, we've shown many, many times, I guess I should put these guys in because that would make it more sense. We've shown many times that this is the Lewis structure of oxygen, and the bond order is 2, so we do have the double bond. It does agree with experiment, but it says it does not agree with Lewis. Well, that's just kind of how it goes when you apply a new theory. Fluorine, we see there's a single bond, and yes, we know there is a fluorine diatomic molecule. Neon 20 has a 0, and neon does not exist. So it's up to you to work some problems. Like I said, I could bore you by going into more detail, but realize paramagnetic has unpaired electrons. Diamagnetic has no unpaired electrons. If given a molecule, you will need to assess it in terms of its bond order and whether it is paramagnetic or diamagnetic. You can use the chart, or maybe you'll get to the point where you can be speedy enough to figure it out at the beginning on your own. So what happens if you have ions? I'm going to say, please do your homework. You will see that certain ions are isoelectronic with certain molecules. I'm going to let you work this out. What if you have a heteronuclear? Well, that is really a case by case and truly beyond the scope of this course. We know that when we do NO, we have 11 electrons, and it turns out that that molecule is very reactive. It no longer has equal mixing. It is closer to oxygen, and MO has better agreement than the Lewis structure. Again, I emphasize, case is what was my case. Your book happens to put in the NO molecular orbitals, and I will let you look at it. Again, we have our atomic orbital of nitrogen, we have our oxygen atomic orbital, and then we have the molecular orbital running down the center. I honestly cannot comment about why the energy levels are the way they are. It is something that's covered in a higher level course. Well, you're going to say, why are we even course doing this? Students also say that. Well, when we have solar energy conversion, those solar panels on people's roofs, you can talk about them having filled molecular orbitals and empty molecular orbitals. There is something called the HOMO-LUMO gap. And when light shines on the solar energy panel, what happens is a promotion of electrons. And as they come back down, there is electricity produced. Take home from our, but probably the more important thing, telling you what molecular orbital theory is, maybe will help you start to see why we have different molecules. One of them is Lipitor, another is naproxen. Lipitor is used to treat cholesterol, if I can spell it, cholesterol. And Naproxen is I'm trying to think, what is it? It is an non-steroidal anti-inflammatory drug. That's what NSAI stands for. So why do people think about things like molecular orbital theory? Well, often when you have a drug, you like to make other derivatives of it and test whether other derivatives have the same, the better, or worse properties. So molecular orbital theory is setting you up for deeper thought on how covalent bonding works. In our class, we only do n=1 and n=2. Let's just say the more bonds you have, the more complications can occur, and it's not for our course. But what I hope